Hello, everyone. Welcome to today's AFMS seminar. It's my great pleasure to introduce today's speaker, Dr. Karthik Sundarraj, who is the Indo-Pacific Technical Manager at Hexagon MSc Software. Karthik holds a bachelor's in industrial engineering and master's and doctorate both in aerospace engineering. His expertise is in experimental and computational fluid dynamics, specializing in the areas of high-speed flows and aerodynamics, with a special interest in electrothermal and biomedical research. And today he will talk about multiphysics-focused CFD modeling for hypersonic vehicles. Over to you, Karthik.
Thank you. Thanks, Vishal. And thanks to AFMC. Thanks for all the participants who are there today on the call. First of all, I think this is a very important topic for the community who will be participating today. Why? One of the reasons is because a lot of simulation technology has evolved around this particular area. And what I really want to speak today is to introduce high-speed flow and how do you handle them, because high-speed flows are quite expensive technologies, not easily replicable. But with the help of CAE, with the help of simulation, I think a lot of things can be achieved. But that again is not a very straightforward approach. So in Hexagon, we have developed multiple approaches to kind of handle this particular area. So I'm very happy and I look forward to presenting what we do in Hexagon for the areas of high speed flow. So today what I'll be touching upon is just a very brief idea about what is CFD heading towards when we talk about high speed flow. Then I'll introduce the different solvers that we have, the density based solver, the hypersonic solvers, and how is it unique and different for us. And there are some validation cases which we'll go through. Then we also will touch upon multi-physics simulation, because gone are the days where we only focus on one physics and then do the entire validation activity. Now all the industries and research institutions are moving towards multi-physics simulation. So let us also see what sort of multi-physics simulation we are capable of doing. And then maybe at some point of time, if you are interested to explore whatever I'm talking about today, then a very brief introduction to how do we solve multiphysics and multidisciplinary simulations, and that may be of interest to you. So very quickly, I think I don't have to reiterate much on this, but I know you all know that hypersonic is going to be the future of many technological growth, both defense and non-defense activities. Mostly countries like China, US, Korea, they have already claimed to have tested hypersonic missiles, and several other countries like Japan, France, Korea, Australia, Germany, they are already developing hypersonic missiles. So that is a very important area. Also, as per the Center for Strategic and International Studies, there is a hypersonic weapon program that is also planned across and specifically focused by the US. So on the other hand, we are not only talking about hypersonic for defense and destructive purposes. Hypersonic and supersonic is also going to be introduced in the commercial market segment. This could be for space travel. These are, I think you are aware of SpaceX, you are aware of Jeff Bezos doing the high-speed flow entry, Richard Branson. So many of them are also talking about using high-speed flow technologies for commercial purposes. This can also be for launch of satellites and various other things. So there is definitely a very important requirement when it comes to hypersonic, supersonic, and all these high-speed flow categories. So that is of critical importance for many countries across the world. So to aid the development of such application, definitely CFD is one of the indispensable tool to design and optimize the shape of the projectiles. So let me address some of the challenges. Of course, CFD is not a straightforward approach, or simulation is not a straightforward approach. So one of the biggest challenge when it comes to using CFD for hypersonic flow is the stability issues. So I think all of you, if you are coming from the aerospace or the CFD background, you may be able to relate to what I'm referring to. But what I mean is that when you run the simulation, the solver, because of the mesh quality and because of various other factors, and in general, the faster the flow, the harder it gets for the solver to converge, especially when the mesh quality is not good or not ideal. So there is a lot of back and forth between the mesh quality, the solver convergence, which has to happen regularly in case of a hypersonic flow. So another challenge is to couple CFD simulation with other physics. It can be structure, because in high-speed flow, there is a lot of fluid structure interaction. You cannot ignore the structural physics when you're performing CFD simulation, or the multi-body dynamics can be another area. Because like I said, we are talking about applications of hypersonic in various areas. It can be a satellite launch vehicle. It can be some pylon separating from aircraft. So there's a lot of multi-body dynamics. There's also a lot of structure involved while this application is being simulated. So we are also looking at having two-way coupling, which is again requires a very cumbersome and it requires a very robust process. So these two challenges often impose a very labor-intensive operation, and the learning curve is quite large. So I think for CFD alone, the learning curve is high. And then when you are coupling multiple physics, definitely the learning curve is very high. So the main requirement is to build a very strong solver and easy and automatic simulation process. If that is possible, then all the challenges that you see, at least the majority of the challenges that you face in a hypersonic simulation can be addressed. Now, keeping that in mind, what we did at Hexagon is we took up these challenges seriously, and we decided to develop a CFD solution that can solve the hypersonic or high-speed specific problems for our client. So first, what we did is we collaborated with the National Institute of Aerospace for several years. Particularly, we partnered with Dr. Nishikawa, who is one of the outstanding CFD algorithm developers. He was also named as AIAA Region 1 Engineer of the Year in 2020. So we jointly developed unique algorithms to achieve this particular goal, which is to provide, first of all, a fast, an accurate, and a robust solver for transonic, supersonic, and hypersonic flows. So basically all the high-speed flow regime. So the details of this solver is something which I will explain in the upcoming slides. And the other point that you need to keep in mind is Cradle CFD, or the CFD tool that we are talking about, is also compatible with other products such as structural, multi-body dynamics in a very efficient manner. We call it as co-simulation or multi-physics simulation. There is a dedicated platform through which you can perform two-way as well as three-way coupling is possible. So this is how we started developing the solver in the area of hypersonic and high-speed flow. There are some reference papers also published. So maybe this slide will be made available to you all later, and you can go through these reference slides. These are very interesting papers on boundary layer resolution, on constructing a diffusion scheme specifically for high-speed flows. Now, talking about high-speed flows, let me very quickly introduce the high-speed flow solver that we have developed exclusively for hypersonic application. So one solver I think most of you may be aware of, this is the density-based solver. Most of you may have come across. This is a standard CFD solver for supersonic and hypersonic flows. So just to quickly introduce the concept of this density-based solver, basically, if you are solving conservation equations, and then you're looking at total density, momentum, and energy. So the density-based solver basically resolves the 5 conservation laws, that is the total density, momentum, and the total energy in a coupled manner. So this approach is very suitable for calculating relatively high speed flows wherever there is compressibility involved or where there is a shock wave that gets generated. It is also possible to compute low Mach number flows like transonic and so on. And density-based solver, like I said, is one of the most widely used method in the aerospace community, whether it is academic or commercial, doesn't matter. Whereas why we are calling this as density-based flow is because if you are already CFD users, you would have come across another solver called pressure-based solver. So density-based solver is basically solving the governing equations for compressible flows where density impact is felt largely. Now, that said, now let me explain what is the scFLOW's convergence accelerator. So scFLOW is known for being fast, robust, and accurate. This is something I already spoke about. So faster convergence means shorter computation time. That's what every one of us really want when we perform a CFD simulation. Therefore, it is also very important to accelerate convergence rate using various methods. So usually a density-based solver requires repeating the steps shown on the right-hand side, what you see in the slide now, which is the convergent solution. At this point, it is extremely important how accurately the Jacobian resolution, right? What you see there, residual. This is a residual which is exactly difficult to obtain, basically, which depends on various physical models. So the scFLOW's density-based solver accelerates the convergence by obtaining the Jacobian at exactly as possible. So we are typically fine-tuning the Jacobian residual. So what we do is we have a state-of-the-art method called Newton-Krylov, which is also implemented for the Jacobian. So in this method, the Jacobian, which is difficult to derive analytically, is obtained by numerical differentiation. So resulting in more stable and better convergence performance. So this is the first step of how scFLOW is faster in resolving and in convergence. Now coming to the next, that is robustness, right, and accurate solution. So stability and accuracy of advection fluxes. This is a very important point. So then that is the next point. So in order to calculate the advection in the governing equation, an advection flux must be selected. So sorry if it is too technical, but I just thought I'll introduce some background of why we say the solver is fast. However, it is generally difficult to construct a very advection flux that is both accurate and stable. So in the figure on the right, what you see shows a comparison between a numerically incorrect solution and a normal solution generated by a shock wave. That is the A and the B. So advection fluxes must be selected so that these phenomenon do not occur. So if you choose a wrong advection flux, there are chances that you may end up in scenarios like A, which is inaccurate prediction. So there are different schemes. I do not want to go into different schemes, but scFLOW already has some very good density-based schemes for specifically addressing the advection flux. Now, this helps us in the accuracy and the stability. Now, lastly, the accuracy and robustness of the diffusion flux. So we spoke about advection flux. Now the other is about the diffusion flux. So in order to calculate the viscous terms in the governing equation, it is necessary to also calculate the gradient on the surface. So the scFLOW's density-based solver uses a alpha damping scheme consisting of an average term and a damping term to ensure that the gradient on the surface can be calculated stably and accurately. So For more details about whatever I spoke, you can also refer to the paper which is mentioned in the bottom of this slide. This will give you a very detailed explanation of whatever basic things which I just introduced to you about the density-based solver of scFLOW. Now, let me take a sample case. So this is a benchmark configuration. So this is an example of how the density-based solver in scFLOW can be used to calculate the Onera M6 wing. So Onera M6 wing case is a very standard and easily available case for validation. And also one of the good thing is these results are obtained with different CFD codes developed as NASA. So NASA has done a lot of validation and it's easy for us to cross-validate this. So two types of computational grids were used. So what you see here is there are two types of computational grid. So one grid from the TMR and the polyhedral grid generated by scFLOW preprocessor. So these are the two grids that we have used. The Spalart-Almaraz, that is the one equation model was used, and the alpha damping scheme, the convergence accelerator, are also introduced in this particular simulation. So what you see as the result shown in the grid, that is the bottom image, the convergence and aerodynamic coefficients are comparable to other calculation codes. So basically, this is one format of validation where we are validating the accuracy and the stability and the performance of the solver by comparing it with already existing benchmarks. So this is one sample case. The other is talking about robustness of the hypersonic solver. So this is a flow where we are doing a transonic flow, which is harder to predict than the subsonic or the supersonic. So at least as per CFD terms, we believe transonic flows are harder to predict because of the various complexities in the transitioning, in the turbulence itself. So whatever example I am showing you is the experimental validation. So this is the experimental case where we have performed this simulation in comparison with many other solvers. So these could be solvers that are developed by research institutions. These can be solvers developed by universities or whatever is present in the universities, or can be a commercial solver which is available in the market. And what you notice very importantly here, let me just switch on my. So what you notice very importantly here is that scFLOW Cradle has proven to be the fastest solver. So while we are also robust, so the robustness is pretty much shown here, and the speed of the solver is being shown here. And this is also a published activity. So you can refer to this link where you can go and have a view at a more detailed report of this entire activity. So I have shown a case study to talk about robustness, accuracy. We also have proven the robustness and accuracy through various experimental benchmarking. Now, so this again, the diffraction of a shock wave. So a very typical example. A shock wave is introduced maybe perpendicular to the inlet region, which is the top. So what you see here is we are introducing a shock wave. The shock wave here is of Mach number 5. And at this very high speed flow, viscous effects can be ignored. So the image on the left is the Schlieren photograph from the experimental reference. On the right hand, you see the animation which is generated by CFD simulation. The animation also clearly shows the distribution and development of the density gradient. So the solver is also able to capture the complex structure of the shock wave and its diffraction very well. So at this point, what you have been introduced to is the unsteady interaction of shock waves take place when a blast wave impinges upon a building or an aircraft. So when the shock wave generated by a sharp energy release in some installation hits the wall, or when the shock wave generated by an exploding gas mixture interacts in a channel. So there are various approaches to really do these simulation. Regular single Mach, double Mach, a lot of things can be done. But what are the key result is the principal finding of all these studies is that if the radius of curvature, that is the front radius of curvature R, is much greater than the radius of the channel, the shock has a high curved profile at the start of the bend, becoming practically plane at the end of the bend. So, I mean, you can refer to the paper here. This is typically going to explain a lot of details about this paper. But what is the message that we want to convey is these kind of physics have a lot of unsteady behavior. There is a lot of unsteadiness in the flow, a lot of unsteadiness in the physics, and a lot of unsteadiness in the turbulence. So you need a highly robust solver and an accurate solver to be able to capture such advanced physics. Now, one is we introduced to you about the density-based solver. Now let us talk about the next important solver, which is the hypersonic solver. So hypersonic solver is something beyond the available density-based solver. So this is a new solver that has been developed and introduced into the CFD software called scFLOW. So let us first understand what is the multiphysics challenge that are present in a hypersonic vehicle. So one of the key issue in the hypersonic vehicle is the heating, the aerodynamic heating. I've already introduced to you the heating could be because of the shock waves that are generated around the object, which are basically flying in high speed. And the flow field behind these shock waves can be thermochemically non-equilibrium in nature. Heating at the surface of the object causes thermal deformation of the object itself. So designing a mechanism to protect the payload and the body itself from external heating is very important in the design of a hypersonic vehicle. So that's the first important challenge. The second is the maneuverability of these vehicles. So you know that maneuverability is already a complex phenomenon even at very low speed condition. Now controlling the guiding surface and separation of objects which are flying at high speed flows are much more complex than that. Third is the material itself. So the material of the entire airframe. It is essential to consider an optimum material for hypersonic vehicle because these are always exposed to extreme environments. There are going to be ionization happening. There's going to be a lot of fluid structural interaction happening. So the environment outside is quite extreme. And lastly, there is also a blackout, communication blackout, which is associated with ionization. So linked to the discussion with the guidance system above, the plasma generated behind the shock wave can also cause communication problem. So these are all the different challenges that a hypersonic vehicle may undergo depending on various applications, what they are going to go through. So first, what we can do is let's look at the results of an analysis where we are assuming an ideal gas is being used in a scFLOW solver. So this is a simulation where the limits of density-based solver is looked at. So density-based solver is limited to certain applications. So we are taking one of the example where the flow condition is Mach 6.1 and the gas considered here is nitrogen. The figure on the left, what you see, compares the shock wave generated in front of the cylinder with an image which is basically an interferometer and the results obtained from an analysis using density-based solver. So what you see is the assumption of ideal gas leads to more distance. So this particular distance in estimating the shock wave position than in the experiment. So experimentally, if you see, or in real sense, the shock wave is much closer. Whereas because we are considering a real gas scenario, you can see that the shock wave is more pushed outwards. So also, if you take a look at the temperature behind the shock wave, as predicted by the density-based solver, so the shock wave causes a discontinuous increase in temperature, but a temperature of 17,000 Kelvin is what is predicted here. So if you see here, this is the temperature behind the shock wave and approximately 17,000 Kelvin. So this is not to say that this value is unphysical, but this is also very, very high. So I don't think that that is quite accurate. So there are various such challenges with considering real gas and ideal gas effects while performing density-based solver simulation. Now, consider the cause of these results. So first, the density-based solver basically assumes an ideal gas. So that is, the specific heat is constant. So that is the first assumption. At a relatively low Mach number, this assumption is fine. I think anything within the range of Mach 5, this assumption of considering ideal gas effect with constant specific is fine. And it is not a problem. Whereas when we are increasing this, but when the relative high Mach number is higher, as in this case, the cylinder case, what you saw, that is about 6 Mach number. The Mach number increases, so real gas effects such as chemical reactions become more important. So therefore, the analysis of the cylinder can be considered to have reached the limit of an applicability of density-based solver. So beyond 5 Mach, or in this case, approximately 6 Mach, density-based solver is no more useful to address this kind of problem. So then what to do? So it is because of that limitation, we from Hexagon have developed the Hypersonic Solver, which is suitable for high-speed flow analysis. So within this Hypersonic solvers, there are different models that are implemented that can more accurately calculate physical phenomena, such as those occurring in the Mach 6 cylinder. So the shock position, the temperature, fluctuations, and so on. So I'll quickly introduce what is this Hypersonic solver in my this slide. So we'll just have a very quick look at how this Hypersonic solver is different from the regular density-based solver. So the normal density-based solver, I've already introduced. It considers the conservation laws of total density, momentum, and energy for each cell. When I'm talking about cell, I'm talking about the mesh. So in contrast, the Hypersonic solver considers conservation laws for each chemical species density, momentum, total energy, and the vibrational energy. So by considering these two energy conservation laws, two temperatures in the flow can be defined. Okay. So these are the translational rotational temperature. So we call it as TTR. And the vibrational electro-electronic temperature, we call it as TVE. Okay. So basically, just repeating once again, we can give two temperatures in this particular Hypersonic solver. So one is the translational rotational temperature. The other is the vibrational electro-electronic temperature. So by using these two temperatures, the chemical reaction rate and the relaxation between the two energy modes can be taken into account to analyze the thermochemical non-equilibrium flow field in a more accurate manner. So this framework is called as Park 2 equation or 2 temperature model. And this has been used many years in the hypersonic coding aspects. So this is a very quick introduction of the Park 2 temperature framework, which has been included in the Cradle's Hypersonic solver. So now we'll take a look at the same problem where we did a density-based solver, and now we look at the same problem being done with a hypersonic solver. So clearly you can see the density-based solver, our results are shown on the left-hand side, and the hypersonic solver results on the right. So the difference is pretty clear. First of all, the position of the shock has been corrected. Now the shock position is very accurate as compared to using a density-based solver. The condition is the same. Also, the comparison of the temperature profile. So the density-based solver is predicting 17,000 Kelvin, and the hypersonic solver is predicting approximately 7,000 Kelvin. Okay, so there is a difference of 10,000 Kelvin between the two solvers itself. So this can be seen that, so what you can see is the hypersonic flow, the temperature distribution behind the shockwave cannot be accurately estimated without taking into account the real gas effects. So anything beyond a more accelerated flow like 5 Mach or 6 Mach, I think the assumption of using a density-based solver with ideal gas may not work accurately, and we need a very dedicated solver to address this particular area of work. So some of the features of the hypersonic solver, the first is consistency with the density-based solver. Of course, we are not creating a completely new solver, but there needs to be a consistency with an existing solver. Most of the features are inherited from density-based solver. One very good case is the alpha damping, the implicit defect correction, which were introduced at the beginning of the presentation. So those are inherited. Therefore, the spatial reconstruction method, the linear solver options are the same. And there is no need to be aware of the changes in these parameters, because the hypersonic solver and the density-based solver, you don't have to really understand the back-end changes. So conventional density-based solver users can handle this new hypersonic solver in a very intuitive manner. So needless to worry that this does not require a dedicated learning curve. It's very much intuitive and as similar as density-based solver. Now, the second solver is stable. One is the derivation of the solver. The second is the stability of the solver. So there are schemes that have been used for many years in the hypersonic area, such as the warming simulation or AUSM family. These are the different schemes. So these schemes are robust in hypersonic flows and allow high reliability analysis. So those are continued to be used. And a third, a non-expert friendly user interface, right? So like I said, you don't have to be an expert in hypersonic field to set up this particular solver. This solver is very easy, even for an existing CFD user, they can go ahead and use this particular feature in the software. Now, let me introduce some of the validations that we have done in the area of hypersonics. So I'm just taking some sample cases. These are all around minimum of 6 Mach. So we are going to talk about 3 cases, approximately 12 Mach, 8 Mach, 38 Mach. So different scenarios and different conditions. So the first one is a comparison with experiments performed in the high enthalpy shock tunnel at DLR. Okay, so the comparison with the experiment is made in terms of surface heat flux and surface pressure. These are the two variables that we are validating. So the grid used in the calculation is shown in the image, the lower right figure. AUSM scheme and FVS schemes, these were what were used for the inviscid fluxes. Least square method, these are all typical setup, and cell-centered gradients are used as per regular methods. Then alpha damping scheme, which is very important, we are using that, and the other limiting factors are being considered. So what you see, this is the result, and we are also comparing this result with the experiment. So the Mach number of the flow is around 9 Mach or maybe 8.9. 5 chemical species are considered in this flow to account the dissociation of molecules. Okay, so I'll not go into the details of what these 5 species are. Now, a comparison in what you see is the surface values between experiment and CFD. That's what you're seeing there. You can see a very good agreement. I don't have to explain. It's very visible that there's a very good agreement between the catalytic and the non-catalytic wall. The surface heat flux also shows that the heat flux is underestimated when catalytic properties are not taken into account. Whereas in case of catalytic properties, the accuracy is much better. So this is one such validation case of a cylinder with experiment. So the second one is comparison of a typical double cone experiment. This was conducted at LENS of CUBRC. So as similar to the previous case of cylinder, again here as well, heat flux and surface pressure are what being compared with the experimental data. Most of the setup schemes are almost the same, except the limiting factor. So here we are using the Venkata Krishna's limiting factor. Otherwise, the schemes are pretty much similar. Now, what you see here is again the result in comparison with the experimental data. So the Mach number here is around 12.59, and there are two chemical species, nitrogen, N2 and N. Chemical reactions are also considered to basically to dissociation of the nitrogen molecules. So the calculated flow field is what you see there, and let me not go through too much here, but what is important is we are able to capture the physics in a very, very accurate manner. The agreement of the CFD code results and the experimental outcome is extremely close. So that is what is very encouraging. Lastly, we are talking about the Fire 2. So this is the analysis of Fire 2. These are high speed flows, which are more than 35, 38 Mach. So this is a 38 Mach condition. So this is a very high velocity flow field. It generates extremely strong shock waves. These cause ionization as well as dissociation reactions. In this case, based on polyhedral cells generated by scFLOW, adaptive mesh refinement are also used to refine the cell in the vicinity of the shock wave, because the shock wave needs to be captured in a very, very accurate manner. So we use this technology called as adaptive mesh refinement. In this calculation, we are using 5 chemical species and 17 chemical reactions. They are all considered for the modeling of air medium, and a comparison was done with the NASA CFD code outcome. So what you see, the middle right side shows the computational grid. So what you see here, this is the computational grid. You can also see there is a focused refinement near the shock layer. This one, what you see here, that is the focused refinement. And what you see in the bottom, these are the heat flux plots obtained by scFLOW, Hypersonic Solver, versus the maximum heat flux obtained by the NASA CFD code. So you can see here, this is the NASA CFD code and cradle. So we are also not deviating too much from the already available validation activity. So now we spoke a lot about CFD, but if you all remember, I also told you the importance of performing dynamic simulation and multi-physics simulation, because all these high-speed flows are not just CFD in nature, but there will be a lot of interaction happening between these physics. So what you see here is I'm just quickly introducing to you the moving mesh as well as shock wave interaction. So what you see here are all the dynamic simulations and how the shock wave interaction happen with the structure while the motion physics is happening. So this is a very simple case of motion in different aspects and then capturing the shock interaction. And this is another motion handling of a two-stage orbiter. So the booster separation simulation, this is also validated with the experimental case where we are capturing the shock waves and then validating the position of the shock wave. This is a Mach 8.1 condition and then performed using the Hypersonic Solver again. So these are the physics which are critical when we are performing high speed flow, because these are all movements, and it's highly important that the solver not only performs high speed flow physics, but is also capable of handling this motion while the high speed simulation is going on. So we do have a reference case here, which is published. You can have a look at this particular case. This is between a delta wing and a sphere, a cylinder in a hypersonic condition. Now we talk about multi-phase, that is coupling, multi-physics coupling. Like I previously introduced, we have something called as the co-simulation engine. Now this co-simulation engine helps us connect multiple physics in a two-way, three-way, or in a one-way coupling manner. So two-way coupling is nothing but performing multiple physics at the same time and crossover of data at the same time. So that is, you do a CFD, you do a structure, and then at the same time, the simulation outcomes are communicated between these two softwares in real time. So the updation happens in real time, and then the outcomes are also in real time nature. So for this sample, I'll take the example of AGARD 445. And then this simulation is talking about the aircraft flutter, the flutter of the wing. And this again is at the high speed flow condition. I'll not go into the details of so most of you may be aware of the AGARD wing, so I don't want to explain too much about this. Now we have created two models. One is the structural model, the other is the CFD model. So like I said, we are going to perform a two-way coupled simulation of a flutter activity. So there will be a structural model generated and the mesh of that structural model, and a CFD model generated, the mesh for that CFD model, and the turbulence what we are considering. So what you see here is the displacement of the wing tip and the trailing edge. Okay, so this is a two-way coupling where the flow is happening. Because of the flow and structure interaction, there is a flutter that is experienced by the wing. Now this flutter is changing the nature of flow, and then the flutter is basically coming from the structure side. So these are the two scenarios where a flow induced structural vibration can be experienced, and this can be done in real time. So what you see here is there are two cases that I showed you previously. Sorry. So first case is there is displacement, enforced displacement, and then the second case is that of a flutter. So these are the different frequencies we are estimating, and then the wind tunnel testing. So this is the wind tunnel test, and we are very close to the wind tunnel test. So if you see here, the estimated flutter is about 13.9 hertz, and then from the wind tunnel, it's 9 and 8. So we are extremely close in identifying the physics while we are performing these kind of co-simulation activity. So if I had done just the CFD, then definitely this value cannot be achieved. But because I'm doing a CFD and the structure co-simulation, that is why we are able to see such close validation of all these kind of fluid structure interaction physics, even at high speed condition. Now, there is also similar cases we have done. This is one case of a missile launch from a pylon. You may be aware of the Eglin model. It's a very famous model for store separation activities. Now, in this case, this is a co-simulation done between CFD and motion dynamic tool. So what you see here is Adams. So the movement of this pylon is defined in Adams, and the flow is basically calculated using Cradle or CFD. So this is a co-simulation done for fluid structure motion dynamic kind of a simulation. So this is also again very critical, again validated with the wind tunnel testing scenario. So with this, I'll come to the last part of my presentation. That is, we do have, while I'm talking about CFD, multiphysics, and multidisciplinary simulation, there is a way that we can support customers, we can support research organizations, institutions by providing a very helpful scheme through which all these multi-physics and multidisciplinary activities can be performed. What we call it is MSc1 licensing. So through MSc1 licensing, various products can be accessed from a single point. So that way you are able to do multiple physical simulations with just one single license. And that is very helpful for the students, for maybe research faculties, different organizations. So they don't have to invest on different tools. So it's just about the tokens which are available. With this token, all these different products can be accessed. And so you can do CFD and structure, you can do CFD, motion dynamics, you can also probably do CFD and acoustics, and all of these for high speed, low speed, any kind of flow physics. So I'll not go into these explanations. Probably I'll skip this and come to my thank you slide. So with this, I really want to thank all of you for this opportunity. I hope I could make justice for the topic that was given to me today. And I'm really happy to take any questions if there are.
Thanks, Karthik. That was a great talk. I'll open it up for questions. Anyone in the audience, please feel free to unmute and go ahead and ask a question, or put it in the chat and I'll read it out. All right, Karthik, we have one question by John Cater in the chat. Can you briefly say something about computational resource requirements, particularly memory, for these coupled solvers?
Okay. So see, that's not a very straightforward question, or there's no one single answer for that. But typically CFD is a compute intensive simulation requirement. So whatever you saw here are all performed on high performance computing platform. Probably used more than 60 cores, sometimes use more than 100 cores, but that does not limit you from not doing these type of simulation, because the same software can also work on 2-core laptops or a 4-core workstation or something like that. But what you're going to be impacted on is the time to do these kind of simulation. So like you rightly asked, you need to provide a lot of RAM space. It's not about the core. Even with 2-core and let's say you have a 98 GB RAM, you will be able to do these kind of simulation. So ideally, my message is you need good amount of RAM. Even with less number of cores, simulations can be done, but will definitely take longer time. If you have more access to HPC and RAM, then the same simulations can happen at a lesser time.
Thanks, Karthik. We have another one from Justin Kin. He says, thanks for the talk. I wonder if for boundary conditions, there are also options to use NSCBC's characteristic boundary conditions for non-reflexive outflows.
Yes, you can define these kind of boundary conditions as well. But typically, since we spoke a lot about hypersonic flows, I did not touch upon a lot of non-reflective outflows, but yes, these are more boundary conditions given to the domain sort of activities, and that can be provided.
Karthik, I had one. How does your hypersonic solver compare with the open source solvers that are available? For example, the Hy2Foam that's a part of OpenFOAM, because it uses the same 2-temperature model by Park.
So that is one of the reasons why I showed you the work done with NASA. There are multiple solvers available, but what makes this Cradle unique is the speed. Okay, so the speed is one of the most critical differentiating factor, even with other solvers. So that is what is the NASA report, where we are talking about comparing, while all these solvers are also robust and accurate, how fast are they when there is necessity to be faster along with being robust and accurate.
All right, I think you're referring to your slide 12, but I mean, in that table, I don't think I saw a comparison with high to foam.
No, sorry, so there is no name mentioned anywhere. You see here, because I don't think NASA is allowed to say what is the name of the solver. So this commercial software or a research institute, this can be any of these softwares.
All right, okay. Because I tried going to that link that is there that you mentioned the reference, but it's all in Japanese, so I couldn't find out which model is what. Anyway, that's fine. Thanks. Yeah. Anyone else has a question? From the audience? All right. If there are no more questions, please join me in thanking Karthik for a great talk. And we look forward to listening more from you, probably in the future seminars.
Oh, yeah, sure. Thank you.